Bam, Mr. True. So, we're finally going to learn where we do all this math and apply it to the real world. Now, you'll be doing this kind of math, at least in this class, a pre-calculus class, or certainly physics and engineering, where, all this trig that we're learning actually does have a real-life application, even if it's hidden by the fact that, computers do so much of this work for us now. So, this is only intro to, like an introduction to vectors. This is only a pre-calculus class that I'm teaching, but, so hopefully these examples I'm about to go over, there's going to be 5 examples of applications of vectors and, putting some real-world settings and looking at some forces that are acting, within that settings. Not sure if it'll be sophisticated enough for some of your physics lessons, if that's what you're watching this video for, but I hope that they do help. So we have an example here. A wagon is pulled by a handle making a 40-degree angle with a force of 35 pounds. What amount of force is actually moving the wagon along the level ground? So let's give ourselves a little quick picture. Not very pretty here, but a couple of wheels, wagon, and a handle. Okay, and up that handle is being applied a force of 35 pounds. Well, that handle, that force is being applied, it's being pulled like you're walking and this wagon's following you along. That force is being applied along an angle of, what do we have here? 40 degrees. So, not all of that 35 pounds is being used to pull the wagon. Actually, with this angle, you're actually kind of lightening the front wheels a little bit. You're wasting some energy in the fact that, at this angle, well, we're only wasting energy in the sense that we're trying to move it along level ground. So, what is that actual force, though? What is the amount of force moving this wagon along the level ground? Well, I'm putting an X here, but when we talk about vectors, my textbook really stresses the horizontal and vertical components. So our vector is going to be written as A times the component vector I plus B times component vector J, and I will switch back and forth between this component notation and this shorthand notation of just simply A and B. That's why I use up so much talk and keep breaking it into pieces. So we're going to find that horizontal component of this vector being here acting as the handle. We have this vector going at 40 degrees, 35 pounds. How do you find the horizontal component? Well, this is just simply going to be a small right triangle. And so thus, how do you find the sides of a right triangle? You just simply do, your SOHCAHTOA. SOHCAHTOA. Based on this angle, what do you want and what do you have? I want the adjacent side, and I have the hypotenuse, so the cosine of 40 is equal to the horizontal component of A over the magnitude of the vector, which is 35 pounds, and we get A is equal to 35 cosine of 40, and 35 times the cosine of 40 is equal to 26.8 pounds. So, if you're pulling that handle with 35 pounds of force, actually only 26.8 pounds of that are helping to move it horizontally along the flat plane. Now, it's not part of this question, but if you wanted to know how much of your energy is lifting up, how much wasted energy do you have, if you wanted to find the vertical component of B, then, well, let's see. Based on this 40-degree angle, B is the hypotenuse, B is the opposite side, and 35 pounds is the hypotenuse. So the sine of 40 is equal to B over 35 pounds, and B is equal to 35 times the sine of 40 degrees, so that ends up being 22.25 pounds. Of force. So with you, again, exerting 35 pounds of energy, or force to pull that wagon, we have some energy in a horizontal component and some energy being used in a vertical component. Moving that wagon, it was 26.8 pounds. Now, what if you wanted to move this wagon a distance of 400 feet? How much work would be done? Well, there's a couple of versions of this formula. The one I'm going to work with is work is calculated by doing the amount of force that's being applied in the direction, well, actually the amount of force being applied times the cosine of the angle times the magnitude of how far you're going to move it. So the force is being applied at 35 pounds. The cosine of the angle, so the cosine of 40 times the amplitude. Now let's just take a second here and look at what the force times the cosine is. The force being applied is 35 pounds, but again, that's not how much energy is being used to move the wagon horizontally along the flat ground or plane. So it kind of makes sense that we're doing 35 times the cosine of 40 because I just worked to that same idea when I was trying to find the amount of horizontal energy or force being applied on that wagon. So that was just basically the horizontal component we just found a second ago. So 35 times the cosine of 40, or the magnitude of force times the cosine of theta, times the magnitude of AB. How far do you want to move it? We want to move that 400 feet. And that answer comes out to, dig out my notes here. Oh, didn't work that out. Well, let's go find that answer, shall we? All right, sorry about that. So we got a total of 10,724.6 foot-pounds of work. All right, let's go on to another example. All right, the magnitude and direction of two forces on an object are 50 pounds at a bearing of south 27 west and 80 pounds at a bearing of north 70 degrees west. What is the magnitude and direction of the resultant vector? Now I'm kind of giving us a little bit of an advanced problem right off the bat. Like I didn't just give you two vectors and ask you to find the resultant. Because if I just give you two vectors and ask you to find the resultant, if they're already in component form, you just add the A's and add the B's, and then you get your answer. This one's a bit difficult because the fact that we're given bearings, and my new current pre-calculus book doesn't do a ton with bearings, just sprinkles it in enough that the kids never seem to be completely comfortable with it. And also there's no drawing. So what we're going to do is we're going to get this drawn, we're going to get our vectors from magnitude and direction into their x and y, or their horizontal and vertical components, add them together then, get a resultant vector, and then convert that back into magnitude and direction so we can actually answer the question, which is what is the final magnitude and the direction of the resultant vector. Okay, well drawing these word problems is always a big struggle, so let's get that drawn and see what it looks like. So we have a north-south line, and we have a vector. They're starting from the same point, so they're going to start about right there. South 27 degrees west. Well, here's south, west is to the left. We're going to do that by 27 degrees, so let's take a look at maybe drawing it something like this. Okay, now that's going to be vector V. It is 27 degrees, or south, 27 degrees west. So there's a little angle in here of 27 degrees. So that's south 27 degrees west. We have another vector which we're going to highlight in blue, that's 80 pounds at a bearing of north 70 degrees west. So north 70 degrees west. I'm going to make this a little bit longer because there's more force behind it. And I'm going to run off the chalkboard as well. So we have an 80-pound force. It's at north 70 degrees west. And the bearing of the yellow one, by the way, we're going to call that vector W. And the bearing, or the magnitude, excuse me, of vector V is 50. Okay, so we've got it drawn. Let's give you a representation of what the resultant's going to look like. So we're going to be looking for, let me finish my parallelogram here that we're starting this drawing off with. And we're going to find the resultant vector, which is down here. And if I've drawn this somewhat reasonable, it looks like there's a downward slope. So this resultant vector, which is going to be W plus V, or V plus W, is going to be in quadrant 3. We'll need to keep that in mind when we find the final direction of this vector. Okay, well, I can't do anything until I have my vectors in the component form, the horizontal and vertical components. And this is the formula, which I showed you in an earlier video, kind of like how it works, where it comes from, that we're going to use to do that. So, vector V is going to be its magnitude, which is 50, times the cosine of the angle. See, our calculators don't understand bearing. You know, it understands standard position rotation. So I need not just the force of each vector, the 80 and 50 pounds, but I need to know the standard position rotation. So remember, standard position rotation is off of the x-axis. So we've got a rotation of what? For vector W, that rotation starts from here and goes 90 and an additional 70. So the angle for W is going to be equal to 90 plus 60, or 160 degrees. But right now I'm working on V. So vector V, I need to know that angle of rotation. Well, it's 90, 180, 270, but I didn't quite make it to the south line. It's 270 minus 27, right? So again, standard position rotation, 0, 90, 180, not quite to 270. I'm shy of 270 by 27 degrees. So for this angle, theta is going to be 270 minus 27, which is 243. Let me just double check that. Don't want to make a mistake. Good. So it's going to be 50 times cosine of 243 I plus, again, the magnitude, which is, I don't need those magnitude symbols anymore, 50 times the sine of 243 J, and then because I can't do that off the top of my head, that's going to come out to be, where am I at? 50, oh, there we go. That's going to be negative 22.7 I plus or minus 44.5 vector J. My book likes to use the IJ components for horizontal and vertical components. So that's vector V. Now we need to find vector W. So W is going to be its magnitude, which is 80, times the cosine of theta, which is 160, I plus, again, 80, sine 160, J, and then vector W is equal to, therefore, negative 75.18 I plus 27.36 J. Now, at this point, we can stop for a second and just make sure that these numbers seem to jive with our drawing. Our blue vector has a negative A value and a positive B value, and thus you can see it's moving to the left and up, so that should be a negative A and a positive B. I've also got my yellow vector going to the left and down, so both my A and B values should be negative, and indeed they are, so it looks like we're okay here. The resultant vector is simply now the result of adding these together. So the resultant vector is going to be taking these two, adding them together, and W plus V, that vector, the resultant vector, is going to be negative 22.7 plus negative 75.18, or just minus, of course, and that comes out to be negative 97.85 I plus a negative, I don't usually write that, I don't know why I have it in my notes, 17.19 J. Again, once you have your horizontal and vertical components, you can simply just add the values of A, add the horizontal components, add the vertical components, and voila. And does this at least seem to make sense? Well, if you draw a pretty decent diagram, we have a negative A value and a negative B value, and that is appeared to be kind of like my drawing where it was slanting down to the left. Again, using my halfway decent drawn diagram to verify the reasonableness of my numbers, and it's also verifying that with a negative A and negative B, that we're in quadrant 3. Okay, let me get this erased and let's move on to trying to find the magnitude and direction of this final vector, but I need more room. So here's our resultant vector. Let's find its magnitude. So we're going to apply our double absolute value symbol, or whatever this thing's called. Well, it's magnitude of a vector symbol. And that is, when we have our vector in component form, we're just going to work out Pythagorean theorem basically. So it's going to be negative 97.85 squared plus negative 17.19 squared. And that magnitude ends up coming out to be, off the top of my head, 99.3. Okay, what about the final direction? Well, tangent of theta, which is equal to B over A. I've been doing the same kind of conversion when you went from, let's say, polar coordinates to rectangular coordinates, and way back when you first started your study in trigonometry, is going to be B, negative 17.19 over A, which is negative 97.85. That is the tangent of theta is equal to, well, how about we just do this? Theta is equal to the inverse tangent of negative 17.19 over negative 97.85. Of course, these negative signs are going to cancel out, and the inverse tangent of that comes out to be 10 degrees. Now, that's all fine and dandy, but 10 degrees is not in quadrant 3. So again, the drawings are important because it not only lets you verify your numbers to their reasonableness as you come along, but now you're like, okay, the calculator said it was a 10-degree direction, but 10 degrees would be over here in quadrant 1. So since we want to be in quadrant 3, which means we need to be just past 180 degrees, and remember, inverse tangent will give you a reference angle. If it has a negative, you can just drop it. I mean, it means something, but as far as reference angles, we only have positive reference angles. So our actual direction is theta is equal to 180 degrees. That's right here, plus another 10. Or, of course, roughly, let's round it off, 190 degrees. So there is our magnitude and direction of our resultant vector. Let's go on to a couple more examples. Bam! Hey, PS. 190 degrees, that is south, SO for south, south, 80 degrees west. Let's do a couple of examples, it won't take so darn long. How about this one? A 2,000-pound object, probably a car, on a 7% or 7.8 degree incline. What amount of force will it take to move the object up the ramp? Well, let's see. How about a, let's do it over here. How about we have a ramp that has a 7.8 degree incline. On that ramp, we've got something, an object that weighs 2,000 pounds. How much is it going to take? And of course, you know, we need to avoid friction, right? So it's glass is service, like ice. No friction. And that object weighs 2,000 pounds. Okay, well, what does gravity do? Gravity doesn't pull us down at an angle. Gravity pulls us straight down to the earth. So we have a vector coming down here that represents gravity, and that gravitational force is 2,000 pounds. Okay, now there's a couple of things going on here. We have the fact that you want to push this object up the ramp, which is going to start at, you know, break even. Basically, how much force does it take to get the thing to be stationary, and there's just anything above that is going to push it up the ramp. And then, you know, what kind of weight is this item actually placing on the ramp? Well, you know, when you get on a scale, your weight again gets pulled straight down in a perpendicular fashion. So the weight of this object is actually getting placed, you know, perpendicular to the ramp. So there's a vector here, which is directly how much weight that ramp is feeling from the object itself. And then there is, and I guess I can have these arrows going in the opposite direction as well. Then you have this other line segment that we want, which is right here. Now, what I'm setting up is we have a vertical direction of gravity. We have a perpendicular angle here to, you know, measure the actual amount of weight that that object is pressing into the ramp. I mean, if that ramp was really, really steep, that object would just fly down the ramp. It would hardly feel any of that weight at all because so much of it would be going down the side or being, you know, cantered off. Oh, and by the way, if you are a physics teacher or you're really advanced in physics, please excuse some of my explanations of this because I do only do vectors for a couple of sections and teach pre-calculus, so I don't have like serious in-depth knowledge of vectors, just what my textbook covers. But we are going to. So you're learning from somebody just admitted maybe they don't know everything. Does anybody know everything? Okay, anyway. So we're going to make this a right angle and then down here a right angle and look at these perpendicular components of the gravity vector. Alright, so this orange vector is going to be the actual weight of the object pressing into the ramp, and then this little segment is going to be the amount of force, and this is what we're concerned about or interested in. Let's just call this, I don't know, A. That little bit of a length there is parallel. That line segment is parallel to that of the ramp because I have alternate interior angles. I have a perpendicular angle here, a perpendicular angle here. I have two lines being intersected and so on, blah, blah, blah. So I have a little right triangle in this corner. Vertical, gravity. The perpendicular, the force perpendicular to the actual surface of the ramp is the weight the object is actually literally pressing into the ramp. That's what that is feeling. And then we have some force here at a slant at the same 7.8 degrees that we have for the ramp itself. And if we find the length of that vector, we're going to find the amount of force it takes to keep this object steady, and then anything greater than that is going to move the object up the ramp. So if this is 7.8 degrees here, then this is also going to be right here. Let's put this in white as well. Right here, this little angle is also going to be 7.8 degrees. So this 7.8, I'm just also like just taking this triangle and moving it, you know, rotating it and flipping it down kind of sort of. So 7.8 here, 7.8 here. Related to the 7.8, this side that we're interested in that's parallel to the ramp is the opposite leg. And the 2000 is acting as the hypotenuse of this right triangle. So what do you have and what do you want? I want the opposite side and I have the hypotenuse, which means that's the sine function. So the sine of 7.8 degrees is equal to the opposite side of A over the hypotenuse of 2,000 pounds. So A is going to be equal to 2,000 times the sine of 7.8, and therefore A ends up coming out to be 271.4 pounds. It's kind of bothering me that I'm using A, which is supposed to be a horizontal component. So let me replace it with the letter F for force. 271.4 pounds, and that's how much force we need to keep the object steady. But the question says, how much force does it take to move it up the ramp? Well, if that's how much force it takes to keep it in balance or equilibrium, which is a concept we're going to talk about down here, I need a force that's greater than 271.4 pounds to start to get it moving up the ramp. Any force greater than that will start to push it up the ramp. Assuming these forces act, this is another question by the way. Assuming these forces act upon the same object, force being, here's force vector 1, 2, comma, -7. And force vector 2 is negative 4, 3. Now I'm giving you these component vectors in shorthand. This is the way my trigonometry book used to have the vectors in there. My new book is always using the I's and J's for horizontal and vertical component. The pointy brackets are just supposed to indicate, you know, the difference between plotting a vector and plotting a point is, well, first of all, it's a ray, and secondly, you don't have to have the initial point on the origin. Well, what do we need to put those two vectors into equilibrium? Well, we need a third vector that when we add all three up, we end up with the zero vector, where there's zero force being applied in a horizontal or vertical direction. Excuse me. So force 1 plus force 2 is going to be equal to, how do you add vectors? You just simply add the A values, so 2 plus negative 4, and you add the B values, negative 7 plus 3. That comes out to be negative 2 and negative 4. Now, what vector could I add to negative 2 and negative 4 to get a resultant vector of 0, 0, a zero vector? Well, all I have to do is change the signs. So this vector vector 2, 4 will put these forces into equilibrium. All right, Mr. True, got one more example. Now for this last example, a plane is traveling 245 miles an hour, that's airspeed, at a bearing of north 63 degrees west. Now the reason why I say this is airspeed, because we're going to have a second force happening, which is wind. Now if you're flying into the wind, your airspeed is going to be faster than your ground speed, because it's, you know, you're flying against the wind. So in relation to that, you're going a certain speed, but that wind is actually slowing you down. Or maybe it's a tailwind and it's speeding you up. The tailwind is blowing at 27 miles per hour in a direction of south, 10 degrees east. Approximate the ground speed, and we're going to also be approximating the direction. This may sound very familiar to the second example I just did, and indeed it is. So I'm not going to actually walk you through this problem. I'm just going to give you the solutions, but give you some time first to try them on your own. So copy that down, and let's see what the diagram looks like. Hope this is what your diagram looks like. Now, I'm drawing my vectors end to end. You can draw your plane vector and your wind vector leaving the same point and draw it in a parallelogram type fashion as far as trying to visualize what the resultant vector looks like. I've drawn mine end to end. So we have a plane vector with an amplitude of 245. We have a wind vector with a force or magnitude or length of 27 miles per hour. And with magnitude, we need direction. Now, not bearing direction, but standard position rotation. So if it's north, 63 west, that is actually going to be an angle measure for the plane vector of 90 plus another 63 degrees, which is going to be 153 degrees. The wind is going to have, now see where the wind is? That wind angle has to rotate all the way around, and from 0 you go to 90, 180, 270, an additional 10 degrees. So the direction for the wind is 280 degrees. So we have our diagram set up. We need to change our vectors from magnitude and direction into the horizontal and vertical components. Let's see if you can do that. One for the plane and of course one for the wind. So to go from our magnitude and direction into our horizontal and vertical components, again it's the magnitude of the vector times the cosine of its angle times vector I, the horizontal component, plus 245, the magnitude of the vector, times the, the sine of the angle, and we get the horizontal and vertical components of negative 218.3 and 111.2. I'm using my shorthand notation here. Well, not mine, but my old textbook's shorthand notation because I'm getting tired of writing I and J all the time. Now look at the white vector. It is going to the left and up, so we should have been expecting a negative a value and a positive b value, and thus we have it. The wind vector going down and to the right a little bit, we should be expecting a positive a and a negative b, and indeed we are. That's equal to the magnitude of the vector times the cosine of its direction, I, plus the magnitude of the vector, in this case it's wind speed of course, sine of the angle direction, times vector j, the vertical component, and you get the shorthand version of negative 1.74 and negative 9.85. Well, now that you have the horizontal and vertical components of each vector, it should be pretty straightforward to find the resultant, because we're just going to add those values of a and b together. And then for theta, again, one more time, this is drawn and you can see that it looks like it's in quadrant 2. Hopefully resultant has a negative a and positive b to verify that it's in quadrant 2. So when you use the tangent function to find out what the angle measure is, make sure you don't just take that number out of the calculator, that you convert it into something that reflects the fact that your vector is in quadrant 2 and not in quadrant, what other quadrant is tangent negative in? So, the resultant of two vectors, when you have them in component form like we have them here, again, is add the a's, add the b's. So, our resultant vector is negative 216.56, comma, 101.35. The magnitude of that vector, again, if you have your vector in component form, you're just working through the Pythagorean theorem. So our final speed, our ground speed, is 239.1 miles per hour, which should make sense, because if you see the way this vector is drawn for the plane, the wind is fighting it a little bit, which is going to slow that plane down some. As far as the final direction of this resultant vector, figuring out what theta is going to be equal to, the tangent of theta is b over a, or 101.35 over negative 216.56. After you do the inverse tangent function, you get negative 25.1 degrees. That's because this vector is drawn in quadrant 2. In quadrant 2, we have negative a's and positive b's, or way back in trig, it would have been negative x's and positive y's. When you set up that ratio of y over x, or now in vectors b over a, if those signs are different, you get a negative answer, of course, or a negative ratio. That happens as well in quadrant 4. So, while this is a good number, it's not going to be our final answer, negative 25.1 degrees. That's, lose the negative and you have a reference angle. The actual answer is going to be, I want to rotate. Remember, reference angles are an acute measurement off of the x-axis, if you will, if you want to place it there for convenience. So I want to rotate 180 degrees and then back off the reference angle, because I'm in quadrant 2, of 25.1 degrees. So 180 minus 25.1 is your angle of rotation of 154.9 degrees. Now, if the whole problem starts off in bearings, your teacher's probably going to want that final answer in bearings as well. So, with bearings, you either reference north or south, and clearly in quadrant 2 we're closer to the degree of north, or the direction of north. So 154.9 is north, 64.9 west. Or take that, well, let's see here, we've got 90, and how do I want to work this out? Oh, well, this reference angle is 25.1 degrees, so I can do 90, which is the difference between north and west. Take 90 and subtract away the 25.1, and you get your 64.9. So, woo! That was a lot of examples. I hope they helped. I'm Mr. True. Bam! Now go do your homework.